All right, so if you work through the activities in that TBIL activity book, they really hammer home this idea that if we have a standard basis vector as one of the columns in our matrix, we can think of that determinant, right, the scaling that's happening by that transformation as having no impact on that particular original basis, right? Like, so my point being, if this had a 0, 1, 0, 0 in this second column, right? If I could do that, this would tell me that the jth component, or whatever, you can think of it that way, has a height or whatever it might be of 1. And so it's not contributing to the overall dimension, right? This is a 4-dimensional thing, but their illustrations were in 3 dimensions, which made life really lovely. It was like, okay, well, that one component didn't impact, so we were able to just look at the determinant of the smaller matrix, as we could just sort of remove that entire component from our situation. So if we want to leverage that idea, what we are hoping for is to have a row or a column in our matrix that is all zeros with a 1. Like, the reason that would help is that I can then do row operations to move that into an appropriate spot. Now, this particular one, I've gone ahead, is a row that is already in what we would hope for if we were doing reduced row echelon form, right? It's in the correct position. Our pivot is in the second row, second column. Everything is lovely. And so let's just see what happens as we do some row operations. So if we were to work on this, right, because right now the row maybe is not as obvious in terms of not contributing to the scaling of whatever this unit thing is. And so let's think about then, I want the column to be the right thing. I want the column to be 0, 1, 0, 0, because then I would believe what TBL showed me. I would feel like I could just toss that information away. But that's fine. That just takes 3 row operations, right? We would need to do row 1 plus 5 of, that's good. Row 1 plus 5 of row 2 as our new row 1. Row 3 would be 7 of that row 2 added to it as our new row 3. And row 4, let's subtract off 3 of that row 2, a new row 4. All right, so then we could do that. We go, okay, sweet, sweet, sweet. Now we have this new matrix. It's nothing is going to change except for we're going to have zeros above and below that pivot. 1, 0, 0, negative 2. Oops, I already want to delete it. 0, negative 2, 2, negative 1. I'm still doing it. 0, 0. Negative 1, negative 4, 1, 0. Cute. Okay, so we go, all right, great. What we did was a bunch of row operations that don't change my determinant, right? So the determinant of my original matrix here, A, is the same as the determinant of this new matrix. We'll call it A1, right? This matrix after doing these first moves. These are going to be the same because every single one of those row operations has no impact on our determinant. We go, sweet. Cool. Now we can say, all right, well, the whole point was I now have a unit piece, so we can go ahead and say, okay, that is not adding anything to the volume, right? It's multiplying everything by 1. We could just, the volume, whatever. It's not volume, it's 4 dimensions, but it's not changing anything. So this, let's make a new matrix. Let's call our new matrix A2, and let's just trim the fat. Let's go ahead. Negative 3, 1, 3, negative 2, negative 1, negative 4, 2, 1, 0. Lovely. So now that we've done that, we can also say this is equal to the determinant of this new matrix A2. So we now have 3 matrices that are all equivalent in terms of their determinant, right? In terms of how they scale the area of something or the volume of something or whatever the 4-dimensional version of volume is. I'm very bad at that. Okay. So the goal here would then be like, well, it'd be great if we could do that again because, well, you might know how to find the determinant of a 3 by 3 matrix or even a 4 by using cofactor expansion, which you can do, or other algorithms. If we want to leverage the same idea, we need to get the same thing we had, right? We need either a row or a column to be all zeros with a 1. And row operations are probably what we're more comfy with. And I think that this particular matrix lends itself towards row operations, right? The one that looks kind of close right now is I at least have a 0 in that row 3. So I'm feeling kind of good about it. It even has a 1 in a pivot position. That pivot's in the wrong spot though. I need it to be in row 2 because it's column 2. So I might take a moment and say, okay, let's do another swap here. Let's say row 1 is going to swap with row 2. Okay? And so now I have this new matrix, A3. And A3 is going to be 2, 1, 0, -2, -1, -4. Those two have swapped places. And we know some stuff, right? We know that doing a row swap like this has changed the determinant, right? Essentially, I've come in and I've said, okay, I'm going to multiply this A2 matrix by this matrix 0, 0, 1, 0, 0. There we go. I said it wrong, but I did it right. We're going to multiply that A2 by that in order to get A3. And so A2, well, we changed it. We changed it by, like, right, if we do the determinants of these things, the determinant of A2 got multiplied by a negative, right? That's what the row swap ends up doing. It changes our determinant because that's the thing we multiplied. So I'm now going, okay, crap. I did change it. We're now at negative, oh, I wrote the wrong thing here, equals determinant of A3, right? So we're now going, okay, going back, because all that stuff was equal at the top, this is now, we're currently at this point. Determinant of A is equal to the negative determinant of A3 or vice versa, right? In fact, it's probably easier to do the negative on the other side. So let's go and put the negative on the other side. This is the thing I struggled with in class, though, that one time where I was like doing the row operations to the result and not to the original, right? Because we want to do that row operation to the OG matrix, not to the result. So that's why that negative on that determinant is happening here, because we're doing that row operation to A2. Keep that in mind when we move to the next step. Okay, so now I don't have an easy way to clear that 2 that I need to go away. I don't know if that you can see my pointer, so I'll go ahead and highlight it. This 2 here, because if I add in that third row, I'm going to add a component. I'm going to add back the number here, and that's going to undo everything. It's just bad. It's just bad. So let's go ahead and try something different. Let's go ahead. Not sure how it's going to help us, but let's take row 3 and let's add row 2 and replace row 3. Right? We know that's not going to change my determinant. So my new A4 matrix going to be exactly the same, right? In fact, instead of writing these all as A4s, I could have written all the elementary row operation matrices and a big old multiplication. I think that's actually what Drew Lewis does in his video, which I'll go ahead and make sure is in the course content as well. But anyway, so now I have this new matrix. I'm going to just throw it in here. -3, 1, 3, 2, 1, 0, and ooh, 0, 0, -4. That worked out nicely. Okay, this is my A4. Nothing has changed here. Adding a multiple of a row to another does not change anything. So let's just update what we have. Our determinant of A is equal to the negative determinant of A. Nothing is new there. Okay, but now we're saying, ooh, we're getting so close. If this was just a 1, then life would be glorious. So we need to do a -1/4 row 4. Oh, it's row 3. Row 3 is my new row 3. Okay, so here's where we have to pay attention to where that operation is happening. The operation is happening to A4. So the determinant of A4 is going to be multiplied by a -1/4 determinant of A4. And that's going to give me the determinant of our result. Right, this is where that one TBL exercise was set up completely ass backwards from what I expected and broke me. So we end up with 0, 0, 1. Right? This is my A5. 2, 1, 0, -3, -1, and 3. That you can't even see my negative. There we go. Okay. So that's my new A5. I know that I can zero out this 3 with a row operation. I also realize it doesn't matter because I did that work last time and it was a waste of my time. So I can say, okay, whoop, whoop. Let me actually fix what's going on up here. So we said the determinant of A4. Okay, well, let's fix this. This is because we need to plug that in. Determinant of A4 is equal to -4 times the determinant of A5. Okay, so let's go ahead, pop this out. Negative times a negative. I'll just go ahead and write it in there. Our new matrix. So we are now at 4 times the determinant of our A5 matrix, which we've now just slimmed down even further to a new matrix. This is getting wild. A6, which is -3, 1, 2, 1. And hey, that's a 2 by 2. We have a formula for that, right? I'll use the little symbols that we see for determinant, which looks like absolute values. This is AD minus BC. So I can come in here and I can say, all right, I actually know the determinant of A6. No more need to do any work. -3 minus 2 is -5. So we get 4 times -5. That should give me my determinant of my original A matrix, -20. Without me needing to like memorize necessarily anything, it's really about that conceptual understanding and our row operations and pulling all of these pieces together. But let's go ahead. I did plug this into Desmos matrix calculator. We can verify, sure enough, the determinant of that original matrix is indeed -20. So obviously doing this in a calculator, significantly easier. But this is one of the two methods. This is sort of the method that is tying everything together. It's probably not what you're going to use, but I thought it was pretty cool because this is why cofactor expansion works. It's why all the algorithms work, is this sort of math going on beneath the surface.